In this video, we'll generate the trendline and trendline polynomial of the binomial series using Taylor-Maclaurin series sum, which uses COMBIN and COMBINA. Here we generate the dataset of the binomial series, which is equal to array formula. The quantity, that's 1 over 1 minus x raised to the power k plus 1, k plus 1. Enter. And the value of k will be data validation, list of items. Let's put there 0 to 5. So at k equals 0, at k equals 1, k equals 2, so on. And we chart this. So insert chart. And we use scatter chart. Check this one. Use row 1 as headers. And series, the trend line, polynomial. Let's put here 48 degree. And show the equations label. Relocate at the bottom. And here's our trend line and trend line polynomial. Next, we generate the Taylor-Maclaurin series sum, which is the summation of a times x to the power n, where a can be a1, the combine of k plus n comma n, or COMBINA, that is k plus 1 comma n. And the value of n will be from 0 to infinity. So it can go as far as 16. The coefficient COMBINA of the COMBINA are formula COMBINA k plus 1 comma n. Then enter. And the combine, which is also array formula. This time we use combine k plus n comma n. And now we can enter the Taylor-Maclaurin series sum. So array formula, series sum of the x values raised to the power n, where n starts from 0, incremented by 1. And the coefficient will be, let's say we choose COMBINA, since they're the same anyway. And here we generate a trendline polynomial of both. So series trendline polynomial to the 8th degree. Show the equation as label. So our approximation is good enough. They are all in the same trend line. We'll calculate the regression coefficients using LINEST. To do that, we complete the LINEST matrix, starting with the power transpose 0 to 8. That's our power. And the elements. So array formula of the x values raised to the power 0 to 8. Then enter. Now we have LINEST for the function itself, the binomial series. That's for data y and data x. Likewise, we do the same thing for the expansion, LINEST data y, and data x. Enter. So let's compare from 0. So they're all the same. This is 1, 1, and for x squared also 1, x cubed also 1, x to the fourth, this is also 1, x to the fifth, 0.96, x to the sixth, 0.96, x to the seventh, 1.48, 1.38, that is 1.4. Continue with 1. Now we have 1 for x to the 0, 2 for x, and 3 for x squared, 4 for x cubed, 4.01, 5.01 for x to the fourth, 5.61 x to the fifth, 5.6.58 x to the sixth, and 12 and 11.9 for x to the seventh, 13.3 for x. Go to k equals 2. So we have 1 for x to the 0, 3 for x, 6 for x squared, 10.07 or 10.1 for x cubed, 15.08, that is approximate x to the fourth, 18.72, 18.73 for x to the fifth, x to the sixth, we have 25.3, x to the seven, 58.9, and x to the eighth, 72. And cube, that's 1 for x to the 0, 4 for x, 10 for x squared, 20.3 for x cubed, 35.4 for x to the fourth, and 46.212 for x to the sixth. Let's say I will change this. Instead of the combina, I will use the combine. Enter. I still get the same results. So we can start with 0. They're the same. From here, the polynomial regression coefficient at k equals 1. Also, the polynomial regression coefficients are the same, except at higher level there's an error already. K equals 2. Okay, still get the same polynomial regression coefficient. K equals 3. Our polynomial regression coefficients are the same. The trend line and the polynomials are the same. This completes the use of combine in the Taylor-Maclaurin's expansion of the binomial series and the LINEST polynomial regression.